In this video, we want to look at two questions on the topic of diffraction and interference. So let's look at question one. So it says, a narrow beam of monochromatic light is passed normally through a diffraction grating of 6 times 10 to the power of 5 lines per meter. 3 spots of light observed on the screen placed 80 centimeters away from the grating. So that's distance between the diffraction gradient and the screen. And then the outer spots are 30 centimeters away from the central spot. Okay, and then determine the wavelength of light used. So basically, the question wants us to calculate wavelength. I think we actually only need one equation for this. So the idea is that I'm going to utilize the ratio of the distances to calculate the angle in which the monochromatic light is diffracted, and then I can utilize that to link back to the d sine theta equation to calculate the wavelength of the light. So in this case, what we know is something like this. This is the slit. Let's say this is one of the slit, and then the idea is that the light goes over here, and then this is the screen. The distance over here is 30, and then over here this is 80 centimeters, and this is the theta. Okay, so because the equation we want to use d sine theta, so I'm going to use Pythagoras. Okay, so in order to create an equation for like sine of theta in terms of the ratio. So basically the hypotenuse will be equal to in the meters, that will be 0.64 plus 0.09, and then which is equal to the square root of 0.73. Okay, and then afterwards, say d sine theta is equal to n lambda. What you want to calculate is lambda, and then in this case, the outer spot, so I assume that's the first order of image, so therefore in this case n will be equal to 1. So lambda will be equal to 1 over, that will be 6 times 10 to the power of 5. And that is in meters, yes. Okay, and then what we do afterwards is the sine of theta. So in this case, sine of theta will be equal to the opposite, which is 0.3 over the square root of this. Okay, and then we will be able to calculate lambda. So in this case, lambda will be equal to let's say 0.3 over, this is the square root of 0.73, and then times by 6 times 10 to the 5, and that is equal to, let's see, 585, yeah. So that will be equal to 585 nanometers. And this will be answer to the question. Now let's see the second question. So over here it says monochromatic light wavelength 600 nanometers incident on 2 vertical slits, hence producing 2 coherent sources. Okay, and then before the light leaving these slits overlaps and interferes, each beam is passed through a tube of 5 centimeters long. Each of the tubes now gradually evacuated. One of the tubes gradually evacuated, and it is noted that the fringe pattern shifts 25 fringes, calculate the refractive index of air. Okay, so the idea is that there's 2 coherent sources, and then so basically each one of them passes through a tube, and one of the tube is air, and the other tube is essentially vacuum as it is evacuated. And then the idea is that the fringe pattern shifts 25 fringes, so that basically means that there's a path difference of 25 wavelengths. And then the question wants to calculate the refractive index of air. So, okay, this is what I'm thinking. Let's say, initially, no, I won't say that. So, the wavelength and then pass through. Okay, so initially, let's see how many wavelengths can actually fit. So basically, the number of wavelengths, let's say x, is basically equal to 5 centimeters, which is 0.05 meters, divided by the wavelength of the monochromatic light. So, wait, there's actually a problem. It says 600 nanometers, but it's the wavelength in vacuum or is in air? It wants us to calculate the refractive index of air, so I assume that it's the wavelength in the vacuum. I think that would be a viable approach. So let's say this is refractive index of air, and then so the ratio of the wavelength will be 600 over the lambda in air. So essentially lambda will be equal to 600 divided by refractive index of air, so therefore that will be 600 over n over here. X is just equal to so this is the number of wavelengths that can fit in the tube with air. Now what about the other one? The other one is 25 fringes. Now in air, the wavelength of light should be shorter. So basically this means that in the vacuum tube there should be less wavelengths. So that will be x minus 25 is equal to 0.05 over the wavelength, which is 600. Oh, I forgot to add. That would be 600 nanometers. This as well. So then we have two simultaneous equations, and then we will be able to calculate n. So if we subtract the two equations, the second one from the first one, that will be 25 is equal to this is the denominator, and over on the top we have what is this is 0.05 n minus 1. Okay, and then we solve for n, so n minus 1 is equal to the other side of that, so that will be equal to 25 times 600 to the power of minus 9, and then down there we have 0.05, and that is 0.0003, and then so therefore the refractive index of air will be equal to 1.0003, and that will be the answer to this question.